So here's a question for you. Let's say I have an object here. Let's say this is a chocolate bar, a Snickers bar, right? And if I were to open it and start cutting it into half, into a quarter, and an eighth, so on and so forth, can I continue cutting this chocolate bar forever and ever? Right? Take a moment to think about it. Hey guys, what's up? Welcome back to the classroom. It's Mr. Low, and today we're gonna go through chapter 7, our model of matter, the particulate nature of matter. So I'm not sure whether you have had the time to think through the question that I described just now, right? So essentially the question is, if I have an object, can I continue cutting this object forever and ever, or is there a limit whereby the thing is so small now I cannot cut it anymore further? Alright, so I don't know whether you have an answer, but this question was asked by a thinker in early ancient Greece. His name is Democritus. So about 400 BC, right? That's very, very far, very, very early in history. Yeah. So he asked this question, right? Okay, can I keep cutting matter into smaller and smaller pieces forever and ever? So you look at this diagram here. I have a big box. Can I cut it into small boxes? Cut it in smaller, and so on. Can I cut it forever and ever? And his answer was no. I don't know what was your answer, right? But he had an argument for that. He had an explanation for that. So he argues this. Number one, if I keep cutting a piece of matter forever and if I keep on cutting, I will eventually cut it into nothingness, right? I'll cut it into so small. Eventually, if I keep on cutting, you cut it into nothingness. Okay, so that's number one. Number two, but if I combine all these pieces of nothingness together, which I get from cutting, the block into very, very small pieces, and I continue cutting, I get nothingness. So if I continue cutting, combining all this nothingness together, I will not get anything, right? Because nothing plus nothing gives you nothing, right? So you realize that there is a problem, because if I started off with something, and after cutting forever, infinitely, I get nothingness, right? And I put back together the nothingness, I put it together, I get nothing. So I started with something and I end up with nothing. So clearly there's a problem here with this argument. So he concluded with all his three statements here, he concluded that there exists an indivisible particles of matter. That means there are particles of matter that we know that's so small that it cannot be further cut down. It's called indivisible, right? And in Greek rather, the language Greek, they call it the atom, which we today know as atom, right? It means the uncuttable. So he predicted that, because back then the technology wasn't that advanced, he just argued that all matter are made up of these indivisible particles called atoms, and that forms the foundation of what we understand in science today. See? Okay, so in this chapter, we're going to learn everything about this thing called this particles, right? So what is the particulate nature of matter? How can we explain the properties of different states of matter using using particles? Okay, and how does particles help us to explain the behavior of stuff upon heating and cooling? And how does the particulate nature of matter help us to appreciate other phenomena of matter around us? Okay, later we'll go through more, but the whole idea is this particulate nature is a model, right? It came out from an argument. Of course, today later I'll show you. Later we are able to see these particles, under a very powerful microscope. So what on earth is this particulate nature of matter? First of all, let's look at this. Look at the title again, right? Particulate nature of matter. Looking at this word matter, right? You should have learned in your primary school what is matter, right? Basically, stuff, right? Okay, let's recall, right? So matter is anything that has mass and occupies space. You occupy space. You are a matter. The pen that you're probably holding now is a matter. How about the air around you? Does it have mass? Does it occupy space? Answer is yes. Okay, so air around you is also a matter, right? Your table, the paper that you're writing on, these are all matter. And everything around you, including yourself, are made up of particles. That's what the model is about, what the theory is about. Okay, so first of all, what are the three states of matter? We have solid, liquid, and gas. Alright, so is rainbow a matter? Why or why not? Okay, answer is no, because rainbow, okay, does not have any mass and does not take any space. Basically, it's just light. This is what we learned in the previous topic, light, right? Light is not a matter, it's just energy. Okay, name a substance that cannot be compressed. In fact, any solid cannot be compressed, right? Means, can you squeeze something even further? Try squeezing the pen that you're holding onto it real hard, real hard. Do you think you can compress it into something smaller? Maybe you can, but answer is any solid cannot be further compressed. We will see why later. Okay, it has to do with the particles. Huh? Okay, so ice, water, and water vapor. You know that these are all water, just that one's solid state, liquid state, and gaseous state, right? But they have very different properties. Why is that so? For example, an ice cube, it has a fixed shape. It's cube. As you made it, right? If you put water into a tray that is cube, right? A hole that is a square, a cube shape, you get an ice that is cubic. But water, you pour it into any container, it just takes the shape of the container, right? You pour it into a tall glass, it takes the shape of the tall glass. You pour it into a bowl, it takes the shape of the bowl. Why is that so? Right? We can all answer this using the particulate nature of matter. Okay? Okay, so yes, we need to understand what happens within a substance, a matter. We need to zoom in down to look at the particles. Okay, so let's find out more. So who on earth? So just now, as I was saying, the Democritus, right? The guy Democritus, he was thinking of the idea of having an atom, a particle that cannot be further broken down or cannot be further cut down, you see. But who was the one who first found the evidence that this particle idea actually works? Right? So it's this Scottish botanist. Okay, botanists are people who study about plants and flowers. Okay, his name is Brown. Okay, and what he did was he was observing a pollen grain. You know, a pollen grain comes from flowers, right? It comes from flowers. Okay, so he was observing a pollen grain put in water under a microscope. Right? What he saw was that this pollen grain was not sitting there still. You see, it was moving around in a very random direction, a very random manner, random direction, random speed. You know, moving around, just jiggling, just moving around. Which he thought, well, okay, maybe the pollen grain had life, right? Because it came from a living thing. But of course, it's not just the pollen grain. Clearly, the pollen grain itself does not have life. So why on earth is it moving? You see, okay. So further down, okay, in history, in the 1900s, Albert Einstein, very famous scientist, very famous physicist, okay, he reasoned that, okay, tiny particles that are these pollen grains, they are actually bombarded by particles that make up liquids, hence they move randomly. Okay, now at this point in time, let us switch over to a simulation to show you what's happening here. All right, so what Brown, the botanist Brown, saw under the microscope is something like this, right? You have the pollen grain, okay, and let me just play this, okay, and you see the pollen grain. What he observed was that this pollen grain was moving randomly. You can see the software actually can trace the motion of this pollen grain. Okay, it's moving really randomly. There's no way to predict where or how this pollen grain will move next. So the question is it really alive? Is it moving by itself? Okay, the answer is no. And what Einstein proposed was this. I'm going to show you behind the scenes. Okay, behind the scenes, what happened is, because this pollen grain is submerged underneath water, isn't it? And in the water, there are water particles. Right, so you see now, these blue dots represent the water particles. So what are they doing to the pollen grain? They're actually hitting onto, bombarding the pollen grain. And as a result of all this bombarding and collision, you can see that this pollen grain is being moved around, being pushed around, right, in random directions. So what Brown managed to see was this. He only managed to see the pollen grain under the microscope, which wasn't powerful enough, but what he did not see was this, right? So this was what Einstein proposed or hypothesized. So we saw just now in the simulation, right, how the pollen grain is being bombarded, right, by the water particles in all directions, okay? And what Robert Brown was only able to see was the pollen grain, Alright, so this random movement of this pollen grains or small particles, okay, suspended, being placed in a liquid or gas, is called the Brownian motion. Of course, he named it. It was named after his surname, which is Brown. Okay, so moving forward. Okay, so a Brownian motion, if you were to draw the diagram, it would look something like this. Okay, so you have the pollen grain here is being pushed around in random directions. So you use straight lines and arrows to represent the path taken by the pollen grain. So of course, besides just pollen grains in water, if you look at dust particles, sometimes you're staring at the window and you see dust flying around. This is the dancing, right? You may describe them as dancing in air. So why is it dust? Why are the dust dancing in air? Right? Are they able to move around themselves? Answer is not. Okay? It's actually the same picture as the Brownian motion, right? What you have is, instead of the pollen grain here, you have the dust particle, and instead of water particles, what do you have? Yeah, you have air particles, right? So the dust being in air, suspended in air, is being bombarded constantly, by air particles in perfectly random direction. Right, so this is how you get, the dancing dust. It's all Brownian motion. Okay, what else? So this is related to the current situation, right? Why are we told to wear masks? Right, because when we sneeze, all the particles from our lung, from our windpipe, your mouth, everything, all the droplets gets airborne, becomes airborne, right? You project it into the air around you, and with the air molecules pushing all these mini droplets that you just sneezed out or coughed out. Okay, these droplets can then travel in air, right? They're airborne now, right? And then as a result, you can pass on diseases and viruses to other people. This is why you're told to wear a mask. Okay, so of course, viral particles do not move in a straight path, but randomly because of Brownian motion, because of air particles bombarding into these viruses. So they kind of push the virus around the place. Okay, so wear a mask so that you don't inhale the virus, sneeze or coughed up by someone else, and using good ventilation, right, will pump out all the bad air or all the viruses out of the room. Okay, so moving forward, okay, why is it that we need to know about Brownian motion? Okay, so Brownian motion, as I was saying just now, was the very first proof that about particles, the first proof of particles, that things are made out of particles. The air, the water, the pen that you're holding is made out of particles, and that all these small discrete particles, they are in constant random motion. That's the keyword here, constant random motion. It means these particles, they are constantly moving, never stop moving, and their motion is random. Okay, and all particles of one pure substance are identical. That means if you're talking about water particles, they're all the same. They all look the same. Whether you're talking about ice, the particles they're exactly the same as water particles in the liquid form and in the gas form. Okay, so this is a modern evidence of particles. Okay, in 2013, IBM managed to manipulate individual atoms. Okay, I will put the video in the description below. Alright, so they actually made an animation, a cute little animation called A Boy and His Atom, the world's smallest movie. Basically, each of these little balls that you see here is a particle. Okay, this view here that you see is zoomed in by a very powerful microscope. I think 100 million times magnification. Go check out the video. Alright, so they actually managed to control these small little particles and create a movie of it. Very, very powerful. Do check it out. Okay, so anyway, what is matter again? Matter is anything that has mass and occupies space, and now we know that matter is made of small discrete particles that are in constant and random motion. Alright, so Okay, so from the particular nature of matter, we can understand the nature of matter, right? So now we don't just see you don't just see a bar of chocolate, the bar of chocolate that I was holding up. Now we see this bar of chocolate is actually made out of these tiny little particles, and so are you, your hands, your hair, your face. They're all made out of tiny little particles that we can't really see, okay, with our eyes. Okay, so they're all in the form of particles. So now you see matter as particles. Okay, so same particles, just now I was saying, right? Same substance, water. The particles are all identical, all the same. So what's the difference between a block of ice, liquid water, and water vapor or steam? Well, the answer is the arrangement of the particles. So let's take a look here. This is a very simple picture illustrating what an ice cube looks like, right? So imagine these little balls here. These are water particles. Okay? Even though they're different colors, they're actually the same thing. Okay, in a solid, it's arranged this way, liquid is arranged this way, and gas, the particles are arranged this way, right? So what is the difference? Okay, at this point in time, let's jump over to another simulation to take a look. All right, so let's look at this simulation here. Okay, we have some particles, and this is actually a solid form of an element called neon. Neon. See if you can locate it in the periodic table. Yeah, right. So you have solid neon particles here, or rather particles of solid of neon that's in solid form. I'm gonna turn it into liquid form now. Notice the difference, right? Okay, look at the spacing between the particles, between solid and liquid. What do you notice about the distances between the particles? You notice that they actually get further apart, isn't it? Okay, I'm going to turn it into gas state now. So now in gaseous state, all the individual particles, they are all the same, right? Still the same particles, but the way that they are arranged, right? Now for a gas mode, right, is the particles are so far apart compared to in the solids. You see, you can see a solid neon is like a perfect square like this. Of course, it need not be, right? But we are just interested in looking at how the particles are being arranged in the same substance, just that they're in different states. Alright, so you can see in the simulation just now how the particles of the same substance are being arranged differently in different states, right? The solid, liquid, and the gas, yeah? Particularly, we look at the distances between the particles. They get further apart, you know, as we change from solid to liquid to gas. Okay, we see more of that later. But first of all, moving on. Okay, so how can we explain the properties of different states, meaning solid, liquid, or gas, using the particulate nature of matter? So what are the properties of different states are we talking about here? Okay, so first, let's look at this table here. You have solid, liquid, and gas. For solids, let's look at the shape, yeah? Solids have a definite shape, a very fixed shape, yeah? So your ice cube, when it's still in solid form, is gonna take a particular shape, the way that you made it, your chocolate bar, right? Your pen, it has a very fixed shape. But liquid, as I said just now, your water, you pour it into any container, it would just take the shape of the container. And so does gas, right? Even though we can't really see how a gas takes the container shape. Okay. So moving for next, volume, right? Volume, we all know what volume is, right? So for solid, definitely we have a fixed volume. For liquid, we also have a fixed volume. But gas, the volume is not fixed. Okay, we can compress the gas. That's what I was saying just now, right? We can actually we cannot compress a solid. All solids cannot be compressed. Liquid a little bit, but not really. But for gas, we can compress a gas. So it does not actually have a definite volume, a fixed volume. Yeah, and compressibility, because it does not have a fixed volume, it's highly compressible. Okay, so sorry, not highly negligible. It's actually highly compressible, right? So a gas can be compressed, but not solid and liquid. So why is that so? Definitely, it has everything got to do with the arrangement of particles in these three states. All right. So yeah, to understand why we go down to the particles, we zoom into the particles and we see why is that so. All right. So this is the table that you may have to fill in certain things in your notes. Okay. So let's take a look. Okay, when we talk about the particles in a substance, there are two things that we mainly need to describe. We need to describe number one, the arrangement of the particles, and number two, the movement of the particles. Okay, so how are they arranged and how they move? Okay, so the arrangement, let's talk about solids first. Okay, so first of all, in a solid, the particles are arranged like this. Okay, so you might want to draw this down in your notes. They are very, very orderly arranged, like very orderly arranged in a rectangle. Actually, it's a cube or a cuboid, right? Because it's three-dimensional. Okay, very neatly arranged, and they're very, very close together. Okay, so the arrangement is such they are very closely packed. They're packed in a very orderly manner, and they have fixed and regular pattern. So you can look at this, right? Very fixed pattern. Okay, so how do the particles move in a solid? Okay, so let's go back to the simulation here. All right, so this is solid state. Under the solid state, that's something we cannot see just now. Okay, look at the particles. How would you describe the movement of the particles? Are they free to move about? Not really. You can see that they're kind of just vibrating at a very fixed spot. Let's look at this guy. Let's look at this guy, right? It's more or less at the same spot, just that it's vibrating. Okay, so to the slides here. Okay, so the movement we use for solid particles, we talk about them vibrating about fixed positions. Okay, and there's something that I did not mention, which is that between the particles, there's actually some form of attractive forces. So between neighboring particles, there's actually a force that is actually holding them close to each other. This is why they are actually arranged in this way. You see, almost as if they are bundled up together. There's a mysterious force that's pulling them together, very close together, right? We call it the forces of attraction between particles. And in solid, these forces are very, very strong. This is why they are held at fixed position. They're not free to move about because they're tied down. They're held very firmly by these forces of attraction. Okay, so this is for solids, right? So as the particles in solid are very closely packed together, okay, the solid has a very definite volume and definite shape. So if we go to the simulation here, you see, no matter how this bundle of particles in a solid, they're arranged such that there is a fixed shape, right? This square shape. So this solid here takes a square shape, definite shape. Okay, and since there's very little space between the particles for them to move closer together, the solid cannot be compressed. This is why I said that solids cannot be compressed, right? So if you look back here at this, can you further squeeze them together? No, you can't because they're really very close together. Let me jump the gun a little bit. For gas, you can continue to press them, you can compress them because there's a lot of space, you see, between the particles, a lot of empty space for them to come closer together. All right, so you are able to compress a gas but not a solid, right? Because there's no space between the particles. Okay, so moving forward, we are now talking about liquids. Okay, so let me jump back to the simulation here and I show you for liquids. Okay, so between solids and liquids, you can see that, okay, the particles are more spaced apart. There's more room for them to move. Right? If you trace one of the particles, let's look at this guy here. Right? It's no longer vibrating at fixed position. It actually can move away from the. It can move right from point A to point B, right? Different points, right? And yeah, the particles further apart from each other. So how do we describe the arrangement? Well, they're still kind of closely packed, even though not very, very closely packed. They're still kind of close to each other, as you can see here, right? For liquids compared to gas, right? Of course, right? So for liquid, they're still closely packed. This time, they are disordered. There's no longer a fixed way of arranging them, right? So it's a random arrangement. Okay. How about movement? Right, instead of vibrating about fixed position, now the particles are able to slide past each other. They can slide, okay? And going back to the forces of attraction between the particles now, is strong, but not very strong compared to solid. In solid, they're very strong, the forces of attraction. This is why they're held at fixed position, you see. But for liquids, since we see that, okay, they're able to kind of move, like past each other, kind of free to move, okay, we conclude that the forces of attraction are not as strong as in solid, right? But we still call it strong, yeah, because we are comparing to gas later on. Okay, so moving on, right? So as particles in liquids are closely packed but disorderly arranged, okay, liquids still have a definite volume. Why does it have a definite volume? Because they're still closely packed. Because it is still closely packed. You cannot further compress the liquid. There's no space to compress, not much, yeah, but does not have a definite shape. Why does it not have a definite shape? Because it is packed in a disorderly manner. Okay, so the particles are no longer held at fixed positions, right? As compared like solid, like particles in a solid, right? So as a result, you see, liquid can take any shape that the container of the container that is placed in. Okay, so it's not first, it cannot be compressed because there is not much space between them to further compress them, right? And at the same time, it does not have a fixed shape here because they are not held at fixed position. They are disorderly arranged. Okay, so we come down now to the very last bit that we need to learn, which is, okay, so let's switch over here and let's look at gas. Now, this is perfect chaos, isn't it? Right? The particles are so far apart from each other and they're really free to move about. Let's trace one of the particles. Oh my gosh, it's really very hard to trace. This guy, apart from colliding with other particles, it's really free to move about as compared to a liquid, right? A particle in a liquid. Right, not really free to move about, right? For gas, they are free to move about. Okay, so how's the arrangement like? Far apart, right? It's disorderly, definitely, right? It's disorderly and random, same as liquid, right? And the movement, now in a gas state, the particles can now move randomly and quickly. By the way, this is how you draw a gas, right? Just a few particles will do. You don't have to draw as many particles as the liquids and in the solid, right? Just a few will do because they're quite far apart, right? So the same container cannot keep so many, okay? So basically, you just draw a few, right? As a rule of thumb, may I suggest for solids you just draw 9, 3 by 3. For liquids, you just draw a few. But oh yes, do take note that for liquid, the particles are supposed to sink to the bottom. Okay, they're not supposed to be hanging at the top of the container because you look at the water in your water bottle, right? None of it is hanging near the opening, the top, right? They all sink to the bottom. So this is how we draw it. But gas, okay, now they're free to move. They can hang around at the top of the container as well. Okay, so back to the forces of attraction. How would you describe them? This time it's weak, you see, as compared to liquid. Now it's weak because you can see that the particles, they're flying all over the place. There's really not much force to hold them down in a fixed position, right? Just like a solid. Alright, so here we go. Okay, as the gas particles are far apart and disorderly, okay, they do not have a definite volume. They do not, because you can compress them. Look at the amount of space between them. You can definitely compress them, right? So you can compress them, therefore it does not have a definite volume and it does not have a definite shape for sure because the particles are not held at fixed positions. So you put a gas into any container, just like a liquid, it will take the shape of the container. Alright, so I hope this is clear enough. So we've seen how the particles are arranged and how they move in all the three different states, yeah? And now we are going to talk about the transition between different states. What happens if you heat up a substance? What happens to the particles when you heat up the substance or when you cool down these substances? Alright, so first of all, let's talk about the energy, yeah? Because when you heat up, you're actually putting in heat energy into the substance. So the substance gains heat energy. When you cool them down, you're actually removing heat energy from the substance. So the substance loses heat energy. Alright, so let's look at what happens to the particles when these things happen. Okay, so when you heat up the substance, the particles gain the heat energy. Clearly, they absorb the heat energy, and as a result, they vibrate more vigorously. Right? They move faster, they vibrate more vigorously, and they start to move slightly further apart from each other. Okay, and the volume increases because they move further apart, and this process is called expansion. Okay, the opposite, let's look at the opposite. Right, when you cool down this substance, right, what happens to the particles? The opposite is the particles lose energy, lose heat energy. As a result, they vibrate less vigorously. You kind of see they become more lethargic. Okay, and they start to move closer to one another. And as a result of them moving closer to each other, the volume of the substance decrease, and the process is called contraction. Let us go back to the simulation to show you what it means. Okay, so now here I have a solid, right? You can see the particles, they are vibrating at fixed positions. They are very closely packed. Let me heat them up a little bit, and let's see what happens. Yeah, so I'm starting to heat it up, and you can see that, oh, okay, first of all, right, they start to move faster than before, right? Can you see? If I reset, this is at first they're just vibrating. Now after I heat up a little bit, you can see that they move more, they move faster, they vibrate more vigorously. What happened to the spaces between the particles? You can't really see here, but if I heat up more, you can see that the object as a whole has expanded. You can see its volume has increased compared to before, right? So let me heat up again. Right, the particles start to move further apart from each other. You can see some spaces, a little space between the particles, and as a result, you can see that the whole object, the whole substance has expanded. Now, over here, there is a common misconception. Let me address this. When we say expansion, when we say an object expands, it is not that the particles expand. No, the particles remain the same shape and the same size. So when we talk about expansion of an object as a whole, actually what happens is the particles move further apart from each other. Right? So bear this in mind, the particles don't expand, they don't contract, they remain the same size. Yeah? Alright, so let's go back to the opposite, right? When you cool down the substance, apply some ice, cooling. So now you see they start to move slower, and they start to come together, and they now vibrate back at fixed positions. Right? Let's heat it up again. Here you can see that they move more, they move further apart from each other, and now I start to cool them down. What happens? They start to slow down, then they come back to an arrangement that's close to each other, fixed position. And let's wait for the last guy to come together. Right. Okay. Of course, you will not get back the same shape as before. You imagine, right? You heat up a block of ice into liquid, somewhat liquid, right? You will take the shape of the container, you just spread out, and when you cool it down back in the freezer, you will just be a puddle, a puddle of ice, right? No longer the same cube as you had before. Okay, so moving back to the slides. Okay, so we see what happens to the particles when we heat up the substance and when we cool down the substance. Notice I use the word particles and the substance, right? So you have the water particles. This is the difference. Okay, do pay attention to this. Okay, so here it goes. Even though the volume of the matter changes, that means the substance itself changes, the particles, they do not. The size and the number of particles do not change. That means the particles do not expand, they do not contract, they remain the same size, and the number of the particles do not change, right? If we go back to the simulation, I'm not going to count how many particles there are, but you do know that when I heat it up, none of them is not going to disappear. The particles are not just going to disappear into thin air. You have one guy escaping, right, but it will come back soon, all right? So the number of particles do not change, right? As a result, we say that the mass of the matter is conserved. Okay, mass, the idea of mass is just how much substances there are inside an object. Okay, so it's related to how heavy the object is, right? So when you heat up or you cool down a substance, the mass of the substances itself does not change. We say it is conserved. We use this word conserve, right? Why is the mass conserved? Because the number of particles don't change. All right, I hope you get the idea. Okay, so let's look at the process of melting, right? So you have solid particles here, neatly arranged, okay, close together to liquid. They are kind of far apart, and the arrangement is not so neat anymore, right? So the question is, big question here, right? How is the change in the model of particles brought about during melting? So what happens to the arrangement and movement of the particles during the process of melting from solid to liquid? Okay, so again, just now when you say, whenever you heat something, a substance, the particles move faster, they gain some kinetic energy, and they vibrate more vigorously. So that's when you heat up a solid, right? Okay, now there's something strange about it. We do know that in general, when we heat up certain things, the temperature should rise, right? Because it gets hotter. But there's something strange here. At the melting point, that means, let's say for water, right, it's at 0 degrees Celsius. When you heat up ice to the melting point, 0 degrees Celsius, as it starts to change from solid to liquid state, you will realize that there is no change in temperature during that process. Okay, during the process of melting, the temperature actually does not change. Okay, if you have the time and you have the thermometer, you can try to do an experiment and see. All right, but there are videos on YouTube for that, so you can keep a lookout. Okay, why is that so? Why is it that the substance temperature does not change during the melting process? Okay, this is because when the particles gain heat energy when it's heated, the energy is used to overcome the forces of attraction between the particles. Okay, now this sounds familiar. Let's go back to the previous slides here. When we talk about the forces of attraction, do you remember this? For solids, it's very strong, right? For the forces of attraction, yeah, very strong. So when the particles gain energy during the melting process, okay, the energy is used to overcome these forces of attraction, and as a result, the particles no longer are held at fixed position because they have overcome the forces. So once they overcome the forces, right, the forces are no longer as strong as before. So this is how it enters, how the substance becomes a liquid. Okay, so the particles so-called break free from one another, from the forces of attraction between the particles. Yeah, and as a result, they can move randomly. So back to the question, why is it that the temperature does not increase? It's because the heat energy gain is used to overcome the forces of attraction. Hence, the temperature does not increase during the melting phase. But after the melting, right, after it becomes fully a complete liquid, fully liquid, you continue to heat it up, the temperature will still continue to increase. No problem. It does not conflict with what we already know. Yeah. Alright, so same picture for boiling. Boiling is also a change of state, just that this time is from liquid to gas, right? So again, during the boiling state, just like melting state, this is something that you can test, right? Boil some water, and you measure the temperature of the water when it's boiling, when you can see bubbles. You can see that it remains at 100 degrees Celsius. It does not increase, you see. So why is that? So again, because the energy gained from the heating is used to overcome the forces of attraction between the particles. So if we go back to the liquid state, you can see that the force of attraction is strong for liquid state, but for gaseous state, it's weak now because they have been overcome by the particles. Okay, because the particles gain the heat energy. Yeah. Okay, so the particles break free from one another and they can now move completely freely. Okay, So again, because the energy gained from the heating during the boiling as well as melting earlier is used to overcome the strong forces of attraction. So as a result, the temperature does not change. Right? So same old story when the substance becomes a gas completely and you continue to heat up the gas, you will see that the temperature will continue to increase. Okay, because the energy is not used to overcome the strong forces of attraction. Okay, so moving on. So now we come to the opposite. The opposite of melting is freezing. Okay, so you realize that um, during the freezing process at 0 degrees Celsius, from liquid to solid, again, there is no change in temperature. That means when you freeze liquid, when you cool down liquid in the freezer, once the liquid reaches 0 degrees Celsius, for some time, the temperature will remain at 0. Okay, because it's going through the process of freezing. Once the whole substance has turned into a solid, okay, what you realize is that okay, you continue to cool it down, it will continue to cool down. The temperature will drop. Yeah. So why is it so? In terms of energy, because when the particles lose energy, this time they're losing, right? Because they're cooling it. Okay, when they lose energy, they cannot overcome the forces of attraction. Right. So as a result, they get overcome by the forces. Right. The particles get overwhelmed by the forces of attraction. They come closer together and they move slower. So this is why there's no change in temperature during the freezing process. Okay, I think at this point in time, maybe it's helpful to go back to the simulation. All right, let's change the water, shall we? Okay, no, maybe not. Okay, so let me look at the temperature here. For solid, for liquid neon, the temperature is 246, right? So let's heat up the thing. Now it's at negative, right? Negative 246. Okay, so as you can see, this is where the melting process comes, right? The solid changes to liquid. Okay, when you supply the energy to the particles, they are actually overcoming. Let's go back here. They're actually trying to pull further apart from each other. They are trying to overcome the forces of attraction. As a result, you can see that once they've overcome more or less, they get further apart from each other. Okay, during this process, you can't really see the temperature here in my screen, but yeah, for you, if I do it slowly, if I heat it up very slowly, you will see that for a brief moment, okay, the temperature actually does not change. Okay, so same goes for condensation. Okay, during condensation, from gas to liquid at the condensing point, which is the boiling point for water, is 100 degrees Celsius. Again, there is no change in temperature for a very brief moment when you cool it down. Okay, this is because the particles come closer, they get overwhelmed by the forces of attraction when they lose energy to the surroundings. Okay, yeah. So as a result, the temperature does not change. Okay, when you condense the gas into liquid. Okay, so let's there's a lot of things here, right? So let's sum up a little bit. Okay, when you heat up a substance, the particles gain energy. Okay, they move faster, they vibrate more vigorously, and they move further apart, right? So that's expansion. Moving further apart means expansion. And the opposite is true. When you cool down a substance, the substance lose energy, they move less vigorously, they come close together, and as a result, you have contraction, right? So that's in general, but we know that we just learned that in the process of changing state, melting and boiling, as well as freezing and condensing, there is no change in temperature. Why? Because it has everything got to do with the forces of attraction. Okay, either the energy gain is used to overcome the forces of attraction in the case of melting and boiling, or the energy loss, okay, by the particles causes them to be overwhelmed by the forces of attraction in the case of freezing and condensation. Okay, so in all these four processes, you observe that there is no change in temperature. Alright, so now we have come to the last part of the topic, okay, which is how does understanding the particulate nature of matter help us to appreciate other phenomena around us. So what is the phenomena that we're going to discuss here? It's about diffusion. Alright, so the idea of diffusion is as such. Diffusion is the movement of particles from a region of higher concentration to region of low concentration. Now, what does concentration mean? Means that there's a lot of, or rather, high concentration means that there's a lot of the same particles in that space. And low concentration means very little. All right. So imagine all of you are being packed in a classroom. 40 of you, maybe 50 of you are being packed in the classroom. Within the classroom space, there is a high concentration of people or students, right? Now, once recess comes, all of you scatter out of the classroom into the canteen or to play your sports or play your video game, whatever. As a result, you can see that the part in class there's the little students left, maybe a few left, all right. So there's now a low concentration of students. So you can see you behave in the same way as particles. You see, uh, at first there's high concentration, a lot of students during lesson time, and when recess comes, all of you scatter into different places, right? So you move to places where there's nobody, right? I.e., the canteen or the front porch where you play your game, right? That's where there's low concentration of people or students, right? So particles move in the same way, and this process is called diffusion. Okay, so diffusion can occur in liquids, can occur in gases, right? So there's this video here that I'd like to go to later. You will see that in this video, the YouTuber actually dropped a few drips of ink into this cup of water. And what do you expect to happen? Well, you can probably imagine the liquid, the red colored ink will start to spread itself out. Okay, and this process is called diffusion, the spreading out of um, the ink in this case, from high concentration place where it just dropped to low concentration, which is other parts of the water that has no ink. Okay, it will just spread itself out until it is kind of evenly distributed, and this process is called diffusion. Alright, so let's look at this YouTube video. Credits to the owner, Dr. SJ, which is this person. Alright, later I'll drop the link in the description below. Okay, let's look at the video. Right, so Dr. SJ is conducting a diffusion experiment. First, I assume it's a she drops some red color ink into the water. Over here, you see this is the high concentration region of ink. The rest low concentration, right? So as a result, you can see that the ink starts to spread itself out from high concentration places to low concentration places. Okay, at times 2 speed, you can see that at the end, more or less, you see the concentration of the red ink is more or less the same, right? So that was warm water, and now she's going to do it in cold water. Look at the process now. Well, there's still diffusion from high concentration region to low concentration region, just that at this time she has to times 4 the speed, right? She has to speed up 4 times, and you can see that the diffusion process is really slow compared to let's compare this to warm water. Real fast, right? The ink is spreading itself out really fast, and for cold water, really not great. You see, very slow even at times 4 speed. Yeah, so that's the idea of diffusion. This time is a liquid, right? From high concentration to low concentration regions. Alright, so you can see from Dr. SJ's experiment what diffusion is about. So that was diffusion in liquid, and now we come to this diffusion in air. Right, so this is how you can smell, okay, a particular scent from far away, right? So I don't know how many of you love or hate durian. It's either one, right? You either love it so much or you either hate it so much. So if you go past a place, a shop selling durian, you can smell the durian coming from the durians, right? Or someone spraying a perfume. Alright, your parents or your siblings, when they spray a perfume on their bodies, you can actually smell it from a distance away, maybe in the next room. Maybe you hate it, maybe you love it, but why is it that you're able to smell this scent, right, from far away? Again, because diffusion, you see. So let's look at this example here, right? When the uncle just opens up the durian, just in the region just around the durian, there is a high concentration of the scent, the smell of the durian, right? A high concentration of the smell because of the particles, right? And due to diffusion, all these particles will start to float away and diffuse into other places where there are low concentration of the smell. So this is how you can get the smell even at a distance away. Okay, so same for the perfume. Yeah, when you just spray the perfume, there's a high concentration of perfume, the particles in that area. Okay, so helium balloon, the balloon that you get for your birthday or whatever. Okay, over time you know that they deflate, right? They're no longer full as you just received it. Don't be sad really, because well, helium particles can pass through the balloons. I think this we kind of know this, right? The air inside, the gas inside actually is helium, right? Again, look up in the periodic table. Helium, right, can escape, okay, into the air by diffusion. And in industries, yes, I was talking about the perfume industries, yeah. Get the perfume, right? So you can smell it from far away because of diffusion. Okay, so there's another in the medical sector. There's a technique called diffusion weighted MRI. Okay, basically, MRI is a scan that scans your body mainly to scan brains for tumors or traumas or impacts. Okay, for people who have gone through some form of concussion. Yeah, okay, used to detect changes in diffusion pattern of water in the body tissues caused by diseases. Now, we do know that a big part of our body, by percentage, about 70% is water. All right, so actually MRI detects the water molecules, the water particles in our bodies. So if someone has some form of diseases, right, the diffusion pattern actually changes. Honestly, I have not much idea because this is medicine. This is medicine. I have no idea. Sorry about that. Okay. But it's used in the medical industry. Yeah. Okay. It also provides the information such as what's the stage of disease. Okay, and then you can inform the doctor what sort of treatment to give. All right, so that's it for this topic. There's a lot of things that we learned today. Let's do a quick recap. So first of all, we learned that things are matter are made out of particles. So now instead of seeing a bar of chocolate, we should now see um, a collection of particles. Yeah, everything is made of particles, including your body, yourself. Okay, and for the same substance, all these particles actually they are the same particles. They are all water particles, for example, just that in different states they are arranged and they're arranged differently and they move differently. Yeah, and as a result of their arrangement, you have certain properties that come out, such as the shape, the volume, and whether the substance in each state, whether they can be compressed or not. Okay, we went on to further look at how the particles are arranged and how they move in solid, liquid, and gaseous state. Okay, so um, we also learned about what happens when you heat up a substance. What happens to the particles when you heat up the substance? Yeah, okay, they move faster and they start to move further apart, right? Okay, um, with the exception of changing in states such as melting and boiling, you observe that the particles actually don't move any faster. Okay, the temperature don't really change, and we know why. It's because of the energy being used to overcome the forces of attraction. The opposite is freezing and condensation, where the energy lost by the particles is as a result of the loss in energy of the particles, they become overwhelmed, right? Or they get overcome by the forces of attraction between each other, and as a result, the temperature does not change. Lastly, we look at one application of this particle nature, right? The particles, which is diffusion in liquid, diffusion in air, as well as the MRI. right? So these are all also kind of like evidence that things, substances, or matter exist in particles. So that's it for this chapter. It's rather short. I hope you enjoy this video, and I'll see you in the next one. Take care.